2 minutes past the official start time, so I guess we can begin. Welcome along, everybody. I think there are still 1 or 2 people arriving as we kick off, but that's fine. And we'll let people arrive. So thank you all very much for coming along to this ITAG AI and Deep Learning Forum event. This is really the first event that we've held in this year of the ITAG AI and Deep Learning Forum. We've sort of rebooted the AI Forum this year, and we're starting into a new program of events. So if you'd like to get involved in and attend future AI Forum events, please check the ITAG website or keep an eye on social media, and please feel free to get involved and to tell colleagues. So today we have a presentation by Dr. Catherine Enright and Jonathan Horgan from Valeo in County Galway. And they're speaking about artificial intelligence at Valeo and visual perception for autonomous driving systems. Jonathan is a deep learning and computer vision architecture manager at Valeo, and he's also a Valeo senior expert. And Catherine is a vision platform functional expert, or functional architect, and also a Valeo expert. So thank you both very much, Catherine and Jonathan, for joining here. The presentation will be, about 30 minutes long or so, maybe 35 minutes. And then after that, or 40 possibly at worst, after that, there'll be a chance for people to ask questions. If you have questions, you can type them in the chat, but we'll wait until after the presentation is over to review questions and to give Jonathan and Catherine an opportunity to answer them. And you can also, after the presentation is over, ask questions by just opening your microphone. So thank you everyone for joining us, and thank you very much, Catherine and Jonathan. Over to you now.
Hello, everyone. If I were to ask you right now, where in the world would you go to work on the next generation AI, state-of-the-art algorithms using the latest deep learning for autonomous driving? Where would you be thinking? Maybe Silicon Valley, somewhere in the west coast of the US, somewhere with better weather than here? I'd hazard a guess that when I say Tuam, County Galway, the first thing that comes into your head isn't quite computer vision and top R&D lab in the world. And yet, here we are. We're one of Galway's best kept secrets. So today, what I'd like to talk to you a little bit about is who we are and what we do in Tuam. What I mean by ADAS, which is the Advanced Driver Assistance Systems, what our current camera-based AI solutions do. And Jonathan will talk us through what the challenges of automotive are and why it's so difficult to deploy AI in the real world. So Valeo, to start with, we're a French multinational company. Last year, they had over 16 billion of total sales. We have over 100,000 employees throughout 33 countries in the world. Although you may not have heard of Valeo, if you drive a car, I'm pretty sure you own a Valeo product. We sell to all the major car manufacturers in the world. So while you might not know us, you know our customers. And we make a huge variety of products. We make windscreen wipers, we make powertrains, we make air conditioning units, we make sensors, ultrasonic sensors, cameras, radars, LiDARs. So no matter what car you drive, I'm pretty sure you'll find one of our products in there. And like all big multinationals, we have to say where we're great. Two of the areas where we're great at the moment, these things change, as you all know, are in electrification. 2 out of the 3 high voltage launches in the last couple of years had our HV solutions. And ADAS, Advanced Driver Assistance Systems, is another area where we're pretty strong. So 1 out of 4 of the vehicles produced since in 2019 had one of our ADAS solutions. And although 1 out of 4 might not sound great, you've got to remember that not all cars are equipped with ADAS solutions. Your lower end cars might not have anything in there. So it's only the higher end cars that typically will be using our products. I think we've already made over 1 billion sensors that have been deployed in cars for ADAS. And over the next 4 years, we're planning on building and producing another 1 billion. And you don't just have to take my word for it that we're pretty good. what we do. The Kpis Awards are, as Jonathan explained to me, they're the Oscars of the automotive industry. And we regularly win these awards for our innovative products. They can be things like lane departure warning, our radar systems, our LiDAR systems. But a lot of the ones that we've won awards for too are based on our camera systems. And cameras is where we work in Tuam. Now, as I say, a lot of people haven't heard about us, but if you live around the Tuam area, you may have seen us. Our test cars are out and about in the town every single day. And we regularly take runs into Galway too. We're looking for odd scenarios, maybe odd car parks, different lighting. So if you see one of these cars hanging around, looking very suspicious, moving very strangely, it's okay. That's just us. Because one of the great things about working in Valeo is that we don't just get to work on the theory and the research and trying things at our desk. We can take our software, throw it on a USB stick, head out to the car and drive around and get a real sense of how it works in the car, how it impacts the driver and the actual end user function that we're trying to support. So as I mentioned, Valeo makes lots of products and on a huge range of sensors. But in Tuam, we're all about vision systems. We're Valeo's Centre of Excellence. And what I mean by a vision system is everything to do with the camera. So we designed the camera from scratch. We manufacture the cameras in Tuam. Then we design the ECUs. And then we design the functions that run on top of the images that those cameras produce. Some of the things we just do are rendering those images in innovative new ways. One of our big products would be a surround view cameras. So by that, I mean, we've got 4 cameras on the car. You'll have one on the front of the car, one on the rear, and one on each of the wing mirrors. So now you get a 360 view around your car. So you've no blind spots anymore. So you can see this, I don't know if you can see my pointer, but here on the right, this is what we call our 360 view. So you can actually take those 4 images of your camera and we render them in such a way that it looks like a top view, like a bird's eye view around your car, which, as you can imagine, makes life very safe. Before you take off on a dark, misty night, you can see, is there anything around my car? Is there a cat after crawling under my wheels or somewhere odd, or some, I don't know, all sorts of things you end up finding under your car. Here in the top is another interesting product we build. This is called Invisible Trailer. So imagine you stick a camera on the back of your trailer. Now, when you're reversing, you can see behind your trailer. So anybody out there who's tried to reverse the trailer will tell you how terrifying it can be. Well, maybe it's just my driving, but I hate driving with a trailer. And looking behind me and you've no idea what's there as you're trying to reverse. So this was our latest Kpis Award we got for this product. So we mount a camera on the back of the trailer, and then you render this view such that it looks like the trailer is invisible to the driver. So as you reverse back, you just look at your head unit and you can see everything around you. Where Jonathan and I tend to focus is down here. This is in the computer vision area. And this is all about taking those camera images and reasoning with them. So most of you here work in the software industry, as you're well aware. A camera image is just a matrix of numbers. And those are different intensities of the scene around you. And while we're very good at interpreting colors and turning them into objects and shapes, and we know what they mean, for a computer, it's actually very difficult. And that's where computer vision comes in. And it's where the deep learning comes in. Before we go further into the deep learning, I just want to have a little talk again about the industry and about what we're trying to do and the different levels of automation. You'd all have heard of autonomous driving. You've all seen the Google car. You've heard of your Tesla cars. But in the industry, there's actually a very well-defined path from where we are now to getting to the top level, which is level 5 of automation. And these are defined here in front of us. So level 0, level 1, and level 2, these are what we call driver support features. And by that, again, that comes back to the term ADAS I used earlier, which is our advanced driver assistance systems. I can't quite say that without getting tongue-tied, but so level 0 to 1, 2, and even level 3, they're all about supporting the driver and sometimes then taking over. So level 0 is really, there's very little automation. whatsoever. You might have a warning signal, like when your ultrasonics beep at you, or you get blind spot warning. Level 1 is when the car actually will do some of the maneuvers autonomously by itself. So maybe it'll steer for a short period, or maybe it'll manage the acceleration. So things like lane centering, some people might have that in their car, or adaptive cruise control. They come in as level 1. Level 2 is the next level up. So here you can have both the steering being controlled and perhaps also the acceleration and deceleration, the longitudinal control we talk about. So if it'll brake, and as well as managing the steering. So that's where you got your adaptive cruise control. Level 3 is where it gets really fun. This is where we call them true automated features. So in these cases, the car is truly taking over. Level 3 is a bit tricky though. Level 3 is the car can take over. It's doing its own thing, but at any moment in time, it may tell you as a driver, you have to drive now. So the driver has to be in the driving seat. You can't quite fall asleep. You can't start watching your movies, because at any point in time, you may have to take over and you may have to drive. Level 4 then, that's where we say, okay, the car is going to drive by itself under certain conditions, and it's maybe in certain places. So this is what we kind of think about when we talk about robo-taxis. So we're not saying the car will drive everywhere. We might have a certain geo-fenced area, and within that area, we say, okay, here it's safe to drive, and the drive can drive by itself. But maybe if it's raining, it won't take over because maybe the sensors won't work as well. But if it's not raining, yeah, we're safe to drive here, or maybe only during the daytime hours. So that's what we mean by in certain conditions and in certain places, the car will drive autonomously. And that's what we refer to as level 4. Level 5 then is the holy grail. And to be honest, nobody thinks we're going to get there. Level 5 is when you have a car that will drive anywhere, at any time of day or night, anywhere in the world, autonomously by itself. That's, I think, will remain the realm of the movies for the foreseeable future. Levels 0, 1, 2, they're already there, and level 3 is already there. Level 4, not so much in Ireland, but it's coming. Those levels are where really determine where we're going and where the industry goes. Like level 1, 2, and 3, I said, that's where we've got today. That's what we've got in our cars today, and we can drive all the time. Your Ubers and your Lyfts, they're working on level 4. They're very interested in those because it cuts their costs. And the vision is that in a few years' time, in major cities and urban areas, there'll be a lot more of these robo-taxis and shuttles driving autonomously around. And that'll be the main form of human transportation. I was at a conference recently, and Dr. Ulison, he's a E-Times journalist, made a prediction. And it'll be interesting to see if it comes true. I thought it was a really nice way of looking at things. He said that by 2060, if you are in an urban area and you want to drive your own private vehicle, you'll have to bring it to a track, a dedicated track, just like we do today with horses. And I just thought it was a nice way of looking at it. We'll see over the next 30 years if that actually comes true, or 30 or 40 years, and hopefully we'll all still be here. But it's an interesting concept that in our urban areas, it'll all be robot taxis, it'll all be shuttle buses. And the idea being that has advantages from a number of perspectives, both from environmental, traffic jams, traffic pollution. We no longer need all these car parks in our cities. How much space do we take up just with car parks for cars that are only used for an hour in the morning and an hour in the evening? So the whole idea is we'll have these robo-taxis. And so these will all be level 4. So they'll have certain geo-fenced areas where it's safe for them to operate. But again, to get to that level of safety, it's expensive and it's going to cost a lot, which is the other reason why we as private owners are less likely to be able to afford vehicles that can achieve that level of automation. The other areas where automation gets really important are for goods transportation. So you've seen, I think even in Arnmore, you can get your takeaway, or could for a while, delivered by drone. So those sorts of delivery services may get more popular, but where the big, huge advantages I see is in trucking, where you've got trucks that drive for thousands of kilometers across empty highways in the States delivering goods. If you can even automate part of that, you've huge advantages, both for the health of the drivers, but for the industry in general. So here's a little video. So a level 3 function, as I said, is when the driver, has to be in the driving seat, but he must be ready to take control at any moment in time. And I've driven features like this in our test cars and in our lab, but I'll never be able to express how it feels. So I'll leave my friends do it for me.
Welcome to the 2021 Cadillac Escalade with enhanced Super Cruise.
Do it.
Nice.
Super Cruise is the industry's first true hands-free driving feature.
One button.
It's that easy.
Welcome to the future.
You ready to roll, bro?
This wolf is ready to go.
I want to drive first.
I don't want to do it.
Let's do this.
Yeah, let's go.
All right, y'all.
I'm so glad Joe's not here, am I right?
Super Cruise is ready to engage.
Wait, we're gonna do this now?
Super Cruise in 3,
Here we go.
2, 1.
Arms up.
My feet are back
Back from what?
from the pedals.
The car, it stopped.
Promise the lane change.
Okay, watch, hold on. It's changing lanes.
Laugh like that.
I know it's doing the thing. What do you think, Joe? Is he doing the thing?
Whoa, why is no one driving? Guys,
Okay, let me try it.
All right, there you go. See? It's nice, right?
I can't believe you're doing this without me. I'm telling Mom.
Bye.
Sometimes you gotta take the wheel and sometimes you just gotta let it go.
You're doing great.
Doing nothing.
Well, since I can use my hands, I'm going to have a cookie.
This is the most exciting thing I've done in a long time.
Get in that driver's seat.
Hey, the stress level is just melting
I
away.
feel great.
It's my turn. Come on, get out.
I love it.
Cadillac. It's super dope. Super dope. That's what I would say.
Guys, I'm still here. All I see is sky.
Welcome to the 2021.
Okay, so part of that feature was developed by engineers in Tune. We supplied the surround view cameras, and we supplied the software that detects those lanes on the ground and those ground markings, and we build the road model based on the computer vision that perceives those lines and lanes. But there's more to any function, obviously, than just the perception. To build any such function, there's a number of building blocks that we typically see, and anybody who works in the industry will be used to a diagram like this. So our first level is what we call our perception level. So this is where we have our sensors and the first layer of intelligence on top of those sensors. So we can have LiDAR sensors, radar sensors, ultrasonic sensors, and these guys in the middle are our guys in Tune, our little cameras. So as well as I mentioned before, providing the cameras, we've the deep learning on top of those and computer vision on top of those to actually understand what those cameras are seeing. So once each of the sensors tells you what they're seeing, you have another layer where you fuse these, because it's always very dangerous to trust just one sensor. They all have limitations. None of them will work in every circumstances. Cameras are pretty useless when it's pitch dark. Every sensor has times when it works and times when it doesn't work. So we always need this fusion layer, which takes the data from multiple sensors and fuses it to have the best perception of the area and be able to reason about the area around the vehicle. And we use that. They build a map to understand what's happening in the scene. Where are their line markings? Where are their lanes? Where are there other vehicles? Is it safe to change lanes? And plan a safe route through all the obstacles in the environment and in the map, because the map is all at this stage that you can see. Then you've got the vehicle control. So you've got to be able to control the steering, you've got to be able to control the acceleration, things like that. Connectivity. Connectivity will become more and more important, especially when we talk about those level 4 robo-taxis. So here's where we might want to download HD maps, really high detailed maps of the area around us if they're available. We might want to talk to the infrastructure in the area. We might want to talk to the traffic lights automatically so they can say, hey, you got to stop now. Maybe there'll be signals in the environment to tell us where the traffic ahead stop, or maybe you'll have cars talking to each other so that a car goes around a corner, he can tell the car behind what's there. They can share their maps. And this is where 5G is going to help us. And when we see that in the car, that you'll suddenly get the bandwidth needed to really benefit from the comms in the car. And finally, the user interface. You've got to be able to tell the driver what's happening, or the passengers, whichever that is. We also might want to be able to monitor them. I don't know, my car tells me when I'm getting too tired, it pops up little messages saying, time for a coffee. Always at the most inopportune moments. And I'm saying, no, I'm not tired. But be able to, your interface to the user and the driver is incredibly important. And it's another area that Valeo have a lot of research in. But from, again, what we do in Tume and what we do with our cameras, these are typically the types of functions that what we do in Tume actually contributes to. You've just seen the highway driving. Trailer assist is another useful function. Let's say you want to be able to connect your trailer to your car and you're reversing and you're trying to line up your hitch and your tow ball. That's where trailer assist can come in. We have cameras that can detect these things. You might want to brake on pedestrians. If somebody jumps out in front of you, you want to automatically brake. First, you've got to know that person is there. So your camera's got to tell you, I see a pedestrian, here's where it is. Automated parking. There's a lot of people out there who really don't like parking their car, especially when it's a tight spot. There's a lot of people that won't even do a parallel parking maneuver. This is where automated parking comes in. And you can get your car based on your cameras. They can see the lines in the ground. They can see where is it safe to park. They can see the objects around. They can see, there's an area that's big enough for my car. You can offer it to the user. The user taps the head unit, says, yep, I want to park in that slot. And you sit back and the car will get in there for you. 360 visualization. Sometimes the most useful functions aren't necessarily the most technically advanced. They're not necessarily the deep learning ones. Just being able to see everything around your car is incredibly useful and a massive boost in the safety for driving. Home parking, that's a pretty cool function. Probably one of the ones I like because I worked in it for a while. This is where some people call it trained parking or home parking. So you buy your brand new expensive car, and because you live in some amazing mansion, it's really such an effort to go from your garage to your house. So the first time you drive home, you drive into your garage, you press the button, you say, just remember where I drove. Just remember the last 200 meters or so. And the next time when I come home, I get the car to leave me at the door. I press a button and say, off you go, park yourself while I wander into my beautiful big mansion. So that's what home parking is all about. It's actually fed by a simultaneous localization or SLAM algorithm. And the same technology can be used not just for home parking, but what we call backdrive assist. So did you ever drive down a really narrow street, come to the bottom and realize, it's a dead end. Now I've got to back all the way out and it's really narrow and really awkward. Well, that's what backdrive assist does. Same idea. You've done a SLAM algorithm. You've recorded your path down the street and now you can reverse back out. But instead of you straining your neck and sweating and panicking as you reverse back, you sit back, you relax, and the car backs out for you. 360 safety cocoon. Again, this is a function which is all about giving you warnings about any objects that are anywhere in 360 around your vehicle. Valet parking. It's another nice one. We're not so bad in Galway, but I remember one Christmas, my teenage children insisted on going to the Dundrum shopping centre just after Christmas. It must have taken us at least an hour, if not 2 hours, to find a parking spot in the parking area and before we could get out of the car to go into some horrible shops. Wouldn't it have been so much nicer if I could have just dropped the car at the entrance and it had done the queuing for me and it had found its parking slot all by itself. And that's where valet car parking comes in. And that's a function that's out there now, that your car, certainly in certain garages, can go and park all by itself and let you do the more interesting things. Charging assist. So this is where if you have a electric vehicle and you want to position it over the charge pad every evening, it'll go and find the charge pad for you. You can see it. We can use our computer vision algorithms to see it and then position the car correctly. Now, some of these functions over time typically have been powered by classical computer vision. But as time goes on, we're using more and more deep learning to enable these functions because it just gives so much better results. But it has its challenges. So this is where I'm going to hand over to Jonathan, who is, I have to admit, I don't like saying it to his face, one of the top CV guys in the world. So over to you, Jonathan. I think you're on mute.
Yep, sorry. Wow, no pressure there, Catherine. Thanks for that. Okay, so yeah, I'm just gonna introduce you a bit to all the, I guess we call them challenges, but they're problems with deploying artificial intelligence in automotive. So this is just a little snapshot of what's actually going into production that's going into production in the next couple of months with a European supplier. So basically, this is a neural network running on our surround view system on all 4 cameras, and we're detecting where the vehicles are, where pedestrians are, where the curbs are, where the ground markings are, where the free space or the drivable area is, in order to build environmental map around the vehicle, in order to be able to automated park, brake on pedestrians, understand where the vehicle can drive, etc., etc. So this is running in parallel with more traditional computer vision that's doing things like structure from motion and what else? Visual simultaneous localization and mapping, which is a traditional computer vision pipeline. So this is something that, yeah, is out there in the market and running in the background. When you see your end user function in the car parking underneath the hood, this is what could actually be happening on the video stream that's coming in from multiple cameras around the vehicle. Okay, so if you go on to the next slide, Catherine. Yeah, so I guess I'm trying to introduce the challenges, I guess, around deploying AI on a little ECU on the left, as opposed to deploying it on, a Google server, or even a simple home server, or even a PC at home is more powerful. So basically, our little device on the left maybe draws 20 watts, which is probably half what your standard, or less than half what your standard laptop draws in terms of power. So I don't think any of the individual challenges of what I'm going to discuss may be unique to automotive. These challenges are seen across the industry in terms of deploying AI. But I think the challenges in terms of automotive, having all of these challenges all at once is pretty unique. So basically, there's a lot of fun, cool challenges, but yeah, it's a balancing act to try and balance all these challenges in terms of hardware deployment, which I'll go into. The other thing I'll say is, I guess there's a massive leap, and some people might say, look, these guys are just doing lane sensing. It's no big deal. I did it in my Coursera course. I got it up and running in a week. What I would say is that there's a massive jump from getting a CNN running on your machine with a data set that you've downloaded, and it's running on an NVIDIA GPU on your machine, and you're getting some results, and it looks nice. There's a huge leap from getting that running to getting something deployed and validated on an ECU into series production on a vehicle. And I can't understate the leap that is. And that's not to say that it's not important to get prototypes up and running. We also get prototypes up and running on PC before we go into series production development, but it is a huge leap. So yeah, if we go on to the next slide. So I guess the first fun challenge is the hardware we have to deploy on. So we're deploying on heterogeneous system on chips, which have custom engines. So any device or any SoC that we have could have, anywhere from 5 to 10 different cores. You'll have an image signal processor which is the first thing, any image that comes in from any camera in our system goes to. It's what demosaics or debayers the image. It does the tone mapping for a high dynamic range image. It does auto white balance, dead pixel correction, vignetting correction, color balancing, everything that's used to create an actual image. So that's just the ISP. That's one hardware accelerator on the device. Then we have convolutional neural networks accelerators, standard GPUs for visualization. We will have ARM cores for general purpose processing. We will have vector engines that are generally used for our SIMD. So as Catherine mentioned, an image is just a matrix. So we obviously have a lot of SIMD operations that we're running across the entire image. So there's engines for helping us do that. Similar to digital signal processors, there's DSPs on these devices. And then there's actually purpose-built hardware accelerators for certain computer vision tasks like dense optical flow or stereo vision, which are basically engines that only do one computer vision operation. And the reason these engines exist is because of the data volumes and throughput. If you were to try and do this processing on general purpose hardware, you would end up consuming the entire thing. So while it's fun to deploy in these heterogeneous systems, some of our algorithms are running across 5 or 6 cores. And the reason they run across 5 or 6 cores is because different parts of the algorithm, depending on the stage of the pixel processing, are better deployed and more efficient on different cores. So it's very easy for everyone to just jump on general purpose processing, but we'd consume it all pretty quickly. So each algorithm has to jump onto the core that suits it best. Obviously, for a convolutional neural network, we would be using the CNN accelerator, but we'd also might be using lens distortion correction accelerators, and for post processing we might be using vector engines. So it's not just throw a CNN and throw it on the hardware accelerator. Even the CNN itself ends up using about 3 or 4 accelerators on the device, and that adds complexity because they all have to be scheduled, and you have to balance the bandwidths between all the algorithms that are running in parallel. So I have a picture of an NVIDIA Xavier board up there, and you can see even the Xavier board has a lot. People consider NVIDIA as GPUs, but their actual devices, their SoCs for automotive or for anyone else, they have multiple cores in there. They have ARM general purpose processing cores, but they also have vector engines and accelerated convolutional neural network accelerators, and they also have purpose-built hardware accelerators for computer vision. Power consumption, I already mentioned. Power consumption and thermal go hand in hand. Our ECUs can be sitting under a piece of carpet in the footwell of the car. So they have to be passively cooled. And when you go passively cooled, you have to keep the power consumption down. Because obviously there's a strong link between power consumption and thermal. So we're generally, we have to power the actual sensors from this device. We have to power the SoC and all the other I/O on the board. So we're talking about devices or a full ECU that may only be drawing 20-25 watts. When we're talking about a surround view system only ECU or a surround view system plus ultrasonics ECU, which is a very low power consumption that we have to meet. And then obviously we're trying to maximize processing power. And the reason we have to maximize processing power is because the sensors are getting, the resolutions are going up, the frame rates are going up, the number of sensors on the board is going up, and we have to try and utilize every single core. The other thing that's happening in parallel with processing power going up is memory and bandwidth consumption is going through the roof, because in the past, when I joined Valeo in 2011, we were dealing with VGA cameras, single VGA cameras, 640, 480, 8-bit depth. So, relatively small. Now, currently, we're looking at 2 and 3 megapixel, 30 FPS, 24-bit depth raw. So the volumes the data sizes have just exploded. The memory consumption has exploded, and the bandwidths required for particularly things like convolutional neural networks that are coming in and out of DDR with large volumes of data regularly means that it's a fine balancing act to try and squeeze everything into the memory footprint of these devices. The other thing I guess we always have to think about is scalability. So there, Katrin mentioned it as well. There's basically your very high-end premium, premium, I guess, OEMs that want all the bells and whistles on their X5 or their Q7 or their S-Class or whatever the case is. But they scale, even within an OEM, it scales back to, you know, BMW 3 Series and 5 Series and X1 and 1 Series and a Daimler A-Class and C-Class, for example. So they don't all get the same functionality, and we obviously can't charge the same amount across that when the functionality decreases or the camera resolution decreases. But we also don't want to have to build entire different systems depending on the car line. So we want to have devices or SoCs and ECUs that are scalable, so that are pin compatible, that we don't have to revalidate all the functions. And that can be a difficulty because you know, when we're dealing with very complex pipelines, we don't want to have to basically re-architect for an individual car line. We also want them to be scalable across OEMs. So when we do a project, we try to make what we call a P2 project, which is basically we try to make an off-the-shelf component that we can supply to BMW and Daimler and Audi and Peugeot, Citroën, or whoever the case is. So you'd be surprised that maybe some functionality that you see in 2 different cars, while the head unit and the display will look very different, underneath the hood it could actually be the exact same algorithm that's running, which is probably news to you that OEMs don't they might actually have the very similar or exactly the same, in some case, perception software running underneath. They may interpret it different, they may display it different, they may use it different, but underneath it could be the same perception. And then there's obviously cost. Cost is a huge factor for hardware deployment, and it's a huge factor for us in terms of if Katrin and I had our way, we would put on the biggest, beefiest SoC on every device and have loads of headroom for doing the cool stuff that we want to do. But unfortunately, cost is one of the main factors for winning projects, and you know, simple things like the amount of DDR or the level of I/O or the number of DMIPs you have on your ARM cores or the frequency they're running at can have a massive impact on the actual cost, the piece price cost, or the BOM bill of materials cost for an ECU, which has a massive impact when you're talking about maybe millions of these ECUs going into SOP. Okay, on to the next one. Thanks, Katrin. Okay, so then that was the kind of hardware challenges, I guess, of deploying AI in automotive. This is the data challenges. So collection of data for training, test, and validation. So there's no real way around installing our cameras and lots of ground truth sensors on a vehicle and going out and capturing data. There's no synthetic way around it. You can't have it completely self-supervised or unsupervised. There needs to be some data captured, and that is a very complex, and it's a project in itself, coming up with there's projects in themselves coming up with the ground truth sensors that we use, and the setups that we use for capturing this data, because the volumes are just enormous. There's the annotation and labeling. So when we capture these images, we need to annotate them and label them for usage in our supervised learning in our CNNs. So maybe there's people labeling pedestrians, labeling line markings, labeling depth, free space, drivable area, etc. And these all have to be labeled in a very time-consuming and costly process. When we talk about data volumes and storage and access, we're talking about, I think, approximately the current download from our vehicle is 1 gigabyte per second. So that means when the car is running and capturing all the data, that includes four surround view cameras, maybe multiple LiDAR ground truth data, the vehicle system bus, some lux sensor data, some GPS data. The full volume data rate of that is about 1 gigabyte per second, and 99% of that is the actual camera data, because that's the largest volume. And so that means you filled your terabyte hard drive in 15 minutes driving around. So when we're talking about data here, we're in terms of storage volumes, we're talking about 10 plus petabytes of data into the hundreds of petabytes of data in terms of storage. And there needs to be an infrastructure around that in order to store it, be able to access it, be able to filter it, be able to download it, and to be able to sift through it to find the data you want, be it for training or validation or test. As I said, reference sensors. So typical reference sensor, you see it on all our vehicles. It's no big secret. Is we use LiDAR data, or Velodyne LiDAR data for ground truth. But even now, the requirements of the OEMs in terms of our perception stacks, the accuracy requirements are almost going beyond our reference sensors. So we're asked to get, centimeter accuracy when our reference sensors might only be giving us close to centimeter accuracy in themselves, and the reference sensors should be possibly 10 times more accurate than the accuracy that our sensors are trying to achieve if we're using them as a ground truth or as a reference sensor. So that's a big challenge in terms of coverage of the vehicle, in terms of reference sensors, and then actual deployment of these reference sensors and getting them to the right intrinsic and extrinsic calibration. Another topic is synchronization. We need millisecond, sub-millisecond synchronization between our reference sensors and our cameras. And there's a bit of infrastructure work around that on the vehicle. We also need data diversity. So we can't just go capturing in Ireland, unfortunately. We can't just go drive around Galway all the time and capture there, because we would end up creating algorithms that fine, they work in Galway and possibly work in Ireland. But if you go to even Europe, not a mind Asia or North America, they won't work as well. Now they'll work in a general case, a pedestrian's a pedestrian, but there's parking slots and road surfaces and structures in Europe, Asia, and North America that look nothing like you would ever see in Ireland. A simple one is bots dots are used for lane marking demarcation in California, which is pretty unique to California, and it's something that doesn't look anything like a line marking. So we specifically have to go and capture those. And the other thing we look at is synthetic data. So we can try and generate synthetic data, and synthetic data is actually a requirement for some of the scenes we're trying to reproduce. OEMs might ask us, how do you deal with, does your system work with braking on a crawling baby, or a toddler in a buggy, or even standard pedestrian testing is difficult to achieve with real vehicle data, because you can't recreate these scenarios because they're simply too dangerous to recreate. So there's always going to be a requirement for some level of synthetic data testing to try and reproduce these scenarios for both training our algorithms, because it's difficult to capture the data for training, but also for recreating scenarios that are too dangerous to capture in real life. Okay. So then,
sorry, Jonathan, I'm just a little bit mindful of time, so maybe if we could wrap up in the next 2 or 3 minutes to give people a chance to ask questions before we finish.
Problem. Yeah, I'll be quick. So in terms of the perception algorithms themselves, obviously that's the challenge that we like the most. We have to stay abreast of the state of the art of computer vision algorithms and convolutional neural networks. We simply have to, because our customers are constantly pushing us for improvements in accuracy, improvements in functionality. So we have to stay aware of that, but that's a challenge we enjoy. As already mentioned, we have to deploy these across complex pipelines across multiple cores on our SoC, and that's not something that's going to change anytime soon, because an algorithm has to make use of the most appropriate accelerator on a device. Functional safety is a huge topic, and the functional safety is becoming more and more key because of the automation levels that Katrin mentioned. So now we're kind of dealing with level 2 automation, but when you move to 3 and 4 in your standard privately owned vehicles, then functional safety is a major topic. And then there's the KPIs. So there's the key performance indicators that our customers are constantly pushing. Availability of the function. They don't want to have the function just running when it's daytime or just running when the weather's nice. They want availability of the function when it's low light, nighttime, raining, foggy, snowing. They want it all the time, and that's what users want, because it gives them trust in a function when it's always available. And then there's the other things, like, I guess, that feed into performance aspects like detection range, detection rate, false positives, and latency. I might skip on to the next one. And then there's, finally, I think this is the challenges of having a training and test infrastructure for all of this. So as I mentioned, we talked about massive data volumes. And when you have massive data volumes, you have to be able to download those massive data volumes. So we're talking about tens to hundreds of petabytes. But we need to download it in order to be able to run it through test software. We can't just store it on the cloud and run it from there. We need to be able to filter the data. So when we're talking about 1 gigabyte per second data coming off the vehicle, we simply can't afford to annotate all the data. It's too costly. So we have to intelligently filter it and only take a very, very small percentage of that data for annotating for training our algorithms. We need to have databases that store all this data, so it's easily searchable, easily downloadable, to be able to test and train on it. And then we have different test methods. Software in the loop is kind of the initial stages of process where we simply just run the software on test data. Processor in the loop is when we have a part of the pipeline running on the processor, but maybe not the entire pipeline of an algorithm running on the processor. That's really important, because software in the loop, some of the hardware accelerators that we're deploying on don't have PC simulations of them, or their PC simulations are simply too slow to be usable because they're hardware accelerated. So in order to be able to use those hardware accelerators as utterly impossible in the development chain, we need to have processor in the loop testing. Hardware in the loop then is we deploy on the actual ECU with all the other functions running as well. That's on a bench, replaying video into it. And then vehicle in the loop is just vehicle testing. And finally, I think the next one. So basically, in conclusion, I guess, to the challenges, the next generation hardware is needed to be able to power the next generation AI algorithms. So there's increases in resolution. We've gone from VGA 10 years ago to 2 and 3 megapixel now, to probably in the next 3 or 4 years, we're talking about 8 megapixel. There's increases in the number of cameras. It was 1 10 years ago. It's 4 to 6 now. We have customers talking about 10, 12, 14 cameras on their devices for SOPs or startup productions in 2025. The levels of automation are increasing, and that's pushing the need for availability, range, detection rates, latencies of our algorithms. So we're currently level 2, level 3. It'll be going to level 4. And they obviously want increased functionality. So they want valet parking, charge pad assists, and all of these functions that make driving simpler. Okay, the next one. I think that might be it. Yeah. So I guess finally, yeah, we're hiring in Valeo at the moment to get the Valeo plugin there right at the end. So yeah, so if you could take a look at the Valeo website if it's of interest to you in terms of joining our AI revolution. And yeah, that's it, I think, Katrin. So yeah, we're open for questions. We'd love to take some questions.
Listen, thank you very much, both of you. It was great to get both this kind of high-level overview of Valeo and what you're achieving, and this, quite in-depth nuts and bolts of the challenges that are facing companies like Valeo to develop. Well, not that there are many companies like Valeo, but company developing autonomous driving systems. And it's phenomenal, really, to think that, you know, in the clip that Catherine showed, that Cadillac's American Super Cruise feature, that the visions systems for that were developed in Tuam, and that there's a team of 600 R&D staff in Tuam doing all of this work. And of course, even though it is a French company, it did originate from an earlier Tuam-based company, Connacht Electronics. So it's not like it was just sort of dropped in there. It's a company that has grown over a very long period in the west of Ireland. And it's really it's a great thing, and is now, you know, a world leader. So listen, we have questions in the chat, and so I'm going to read a couple of questions in the chat, go back over them, and maybe Catherine and Jonathan can jump in to answer. People can then add other questions in the chat, or they can open their mics to ask. I'm mindful this is lunchtime for people. We need to wrap up in the next 7 or 8 minutes. So Bernadette asked, has there been progress in the last couple of years at EU level in legislation to allow automated driving features at level 3 and beyond to be adopted? With either of you know?
I know it's slow. It's very slow. Customers are generally looking at level 2 plus systems, and only on their very premium lines looking at level 3. So
is legislation an issue?
Yeah, 100%. Yeah, it's been delayed and been delayed. I think they are looking at regulations, the UK and EU, on adaptive cruise control and lane change assist regulations, but I think that is definitely hindering deployment of level 3 in Europe. Okay. So, you know, we talked about it in Cav Ireland group, trying to get level 3 testing opened up in Ireland, and I think it's still on. I think COVID probably delayed it a bit. So, but yeah, it is an issue, 100%.
Thanks. Rita asked about whether vehicle platooning is already in the market, where vehicles communicate to surrounding vehicles.
Because I'm not aware of it in the market.
Okay.
No. Certainly an area of research.
I would have thought so too. I mean, I think current generation network systems aren't quite reliable enough or constantly available enough. Yeah. Xiaolin asked, are the pipelines interesting on the vehicle programmable for dividing the data stream from centers and codecs to the CNN offloading, or does is it all sort of hard coded, or how does it all work?
So parts of it are okay. So like something like the lenses or the ISP is effectively hard coded. You can turn on and off parts of the pipeline, and you can change parameters, but it's a hard coded pipeline. The lens distortion correction, again, it's an accelerator for doing mapping. It's limited use, but you can change how the correction is done, and you can change the level of the correction and the resolutions of the outputs, etc. So that's relatively hard coded. The ARMs are freely programmable, DSPs are freely programmable, and the vector engines are freely programmable. The convolutional neural networks accelerators are generally hard coded as well. They would have some fixed restrictions that we would have to employ when we're building our network or we're designing our network architecture. Maybe the convolutions will be blocked. They wouldn't have some of the latest and greatest innovations in terms of network architecture, because remember, these convolutional accelerators may have been built, 3 or maybe started research 2 or 3 years before they're actually deployed, and therefore the deep learning is advancing so quickly that it won't be able to keep up with them. But so they're generally hard coded, and that's how you get the acceleration, is that you hard code them. They're basically like ASICs.
Sure. That actually was a related question I had myself that wasn't in the chat now. I mean, you mentioned, Jonathan, there's a huge leap in going from something running in your PC and a GPU to getting it running in a car.
Yep.
I assume there's a big leap in having something running in a Jupyter notebook in Python to deploy it in a car. So what kind of programming languages are you using?
We use standard programming language. So we use Python. Okay, so we use Python for convolutional neural networks, and we try to use some SoC suppliers have kind of custom descriptions for their CNN accelerators. Some use like generic formats like ONNX but we use Python, and we use things like what everyone uses, PyTorch and
Okay, great.
like
I wasn't sure they'd be available to you. That's good.
Yeah, PyTorch. We used actually TensorFlow with a Keras back, or a Keras with a TensorFlow backend at the moment, and we're kind of generally moving to PyTorch now at the moment. Yeah.
Someone asked Mike whether 5G rollout. Do you see a time when processing will move to the cloud, or will it stay on the vehicle?
Maybe Katrin, do you want to take one?
Yeah, it depends on what you're trying to do. I mean, if you have a pedestrian walking in front of you, are you going to get the answer back from the cloud? Are you going to be able to share those images quickly enough with the cloud and get the answer back in enough time to be able to break in time?
And depend on the connection not breaking down or whatever. Yeah. So
exactly. So there's always going to be some processing done on the car for critical things like that. But you will see things like the map sharing certainly will be in the cloud, and map building where you would share all the data with the cloud. But then even at that, some of the processing might still be done on the car, or you might just share your objects rather than the whole images. It'll vary, and it'll depend on the reliability we can get.
Thanks for that. Emir asked about how to deal with bad quality images, such as if there's rain or dirt or low light and somewhere. Do you have to do filtering, or do you try to address it at the hardware level?
So for low light, okay, so we maximize low light performance anyway for video to the user. It's not just for perception. It's an issue at the moment because everyone's pushing resolution up and up and up, and they want to keep the camera the same size. Therefore, the pixel pitch is getting smaller and smaller and smaller, and therefore we are capturing less and less light per pixel, which is increasing or decreasing our SNR. So low light, yeah. So we it's getting harder. So but the image vendors then are trying to push quantum efficiency and stuff so that we get better images. So they're managing to increase the resolution and still managing to maintain, despite the pixel pitch size dropping, they're still managing to maintain low light sensitivity. In terms of us, I guess what we're doing is in the future, we're looking at trying to have our own ISP path. So independent of having a human viewing path for doing the image signal processor, as in from the raw exposures, multiple raw exposures, 2, maybe 3, depending on the HDR imager. Getting from those 2 or 3 exposures to an image is one path will be for human viewing, and maybe we'll have another path that will be completely optimized for computer vision, which means that we can do things a little differently, because the image a human sees as good is quite often a lot different than what computer vision can look at as good, and that will increase our low light sensitivity.
Great, thanks for that. I've got 2 last questions, and I'm going to ask them in reverse order. So one is from Patrick, who Catherine said that level 5 automation will, be sort of effectively sci-fi. What is the main blocker between level 4 and level 5?
It's the working anywhere in any conditions, and the level of sensors you're going to need for that. Like, we've all driven down back dodgy roads in Connemara. They're not even going to be mapped properly. There's not going, not that many cars will have driven there before you, and then some random sheep goes out in front of you. Not many algorithms at the moment are trained on sheep, and there is a lot of call for kangaroos and deers and things like that do actually cause a lot of accidents. But the main blocker is getting it everywhere, and the cost to do it. I've heard one quote was, the amount you'd need to spend, the people who'd be able to afford a level 5 vehicle with all the sensors that would be required, well, they can afford to hire a driver.
Fair enough.
So why do you need it? Where's even the market for it?
That's a fair point. That's a good point. And then there was the last question, which was, Ethan asked, what sort of positions are available for working in AI, and what kind of qualifications or experience would you require?
There's positions, there's deep learning engineer positions and deep learning architect positions. Look, generally we require some sort of maybe some deep learning experience in the industry, for sure helps. A master's in deep learning and hopefully rolling out in the next couple of months. We're looking at a graduate program as well. But the positions that are open at the moment will generally require, you know, a couple of years deep learning experience, or a deep learning master's, or maybe a degree with some final year project that had deep learning as an aspect would help as well.
And I suppose I should mention that NUI Galway has masters in artificial intelligence.
Exactly, very good one. Yeah.
But we should also mention that we don't just need the deep learning engineers.
Sure.
We also need testers. We need managers. We need a whole suite of people to get these deployed in the car.
Great point.
Yeah, there's quite a few positions open in Valeo at the moment. Yeah.
Listen, thank you both very much for all of your time. I really appreciate it. Thank you also everybody who participated and asked all the questions. Are really great. I guess we're out of time really, so we should wrap up there. But thanks again, Catherine and Jonathan. It was really interesting. I thought fascinating and great to learn about what's happening in Valeo at the moment. Well done to you both.
Pleasure.
Thanks for the invite.
Thanks a million.
Very welcome.